Hi, in this video I will show you the automatic mesh refinement in SCIA Engineer and the things they have influence on the precision of the finite element analysis in SCIA Engineer. My name is Ivan Beleš. I have prepared more models. One of them is such small house, and in this model, I will show you how you can handle this automatic mesh refinement. So first, you can go to Setup, Mesh, and then you can define the average size of the 2D elements. Usually, it will, we say the thickness of the slab to double thickness of the slab. But we don't know really before we do a calculation how precision is this. So, and the global accuracy and the precision of the model will calculate the automatic mesh refinement in SCIA Engineer. So to activate it, you go to use automatic mesh refinement, and then you set the maximal, the target error which you want to achieve in the calculation. For this, you need loads, because the error is calculated as an energy or energy density over integration of stresses and deformation. And for the stresses, we will need the loads, of course. So it's defined, and then you can directly go to calculation. For the first calculation, the standard mesh for with our 40 centimeter elements will be used. It's quickly finished, I hope. Okay. And now we get the accuracy, the quality of the numerical solution is 21.5%. It's not very good for me because my target was 10%. So I use target between 10 and 15%. After you have this calculation, you can directly click on the mesh generation, and then SCIA Engineer will automatically refine the mesh. But I will show you why SCIA Engineer will do it. And you can find it in this menu in results to the members results and numerical error. And then you see the energy density joule per cubic meter for each element. And from this, you can see where you have troubles in your model. So these areas with the red value are not very good. So we can go to the clipping box, and I go a little bit down with the clipping box. Then you see the problem points. So you can then see where you have troubles. Maybe you have not exactly created the geometry, then you can correct it and calculate again. Or if you say, no, my geometry is okay, then you can run the mesh generation, and after this, SCIA Engineer will make the element smaller. I have forgotten to show you in the results. We can do it in next step. In this menu for the, I will show you the mesh. In this menu for the energy density, there is also a property where you can look on the element size which you need to get this 10% error. So, and you see SCIA Engineer automatically created smaller elements, and with these smaller elements we can calculate the structure again and look on the precision, and if it's okay, then I can stop the calculation, go to dimensioning. If not, you can again generate mesh and run the calculation. So in these steps, calculation, mesh generation, calculation, mesh generation, until you are finished, you can get your exact or more exact mesh. Okay, we have 13% from 22 or 21% is not so bad, so I am between 10 and 15%, so I personally am satisfied. And in this menu, instead of numerical error, you can also look on the mesh refinement, and then you see the size of the elements you need. For example, where nothing happened, because where the stresses are constant, then you don't need a smaller mesh, or you need small mesh only where you have big gradients of the stresses. So you see in this plate or in this wall there is no loading. In the wall we need 80 or 90 centimeter big elements, and in these corners we need something about 10 centimeters. So, and do I have the results? Yes, okay. So now I am finished. I can go to dimensioning. This is a small house. It's in 3D. You don't have so much possibilities to make it better. You can prevent these singularities. For example, if I go to clipping box around all entities. So, and make it smaller. Of course, that was not a very good idea to place this column near the opening or near this corner. Then you have troubles with punching and also with big stresses. And you also see here we have some wall. Would be maybe better to continue with the wall with a rib, and then the stresses would be better. But if often you will calculate also smaller models, and on the small model I can show better which things have influence on the calculation. Okay, first model, I have a simply slab, and I will change all these supports to rigid in Z direction. This is standard, how you usually calculate. I will look on the mesh settings. Okay, the automatic mesh refinement is activated. We have again the same size of elements. Something between plate thickness and double plate thickness is a good start point, which will be usually used for the calculation for buildings. So, and after the calculation, we get 22% accuracy, which is not very good. What we can do, we can look on the mesh. This is the standard mesh. I can start the mesh generation. Mesh will be smaller, and with this smaller mesh, I run the calculation again. And now I have something between 14 and 15% accuracy. I would say I am satisfied. What if we change the supports from rigid to flexible? What is the stiffness? The stiffness, this is the Hooke law. The stiffness is the thickness of the plate multiplied with the Young modulus of the material of the wall, multiplied with the Young modulus of the material which is used for the wall, and divided by the height of the wall. Of course, if you have stronger material, you have stronger spring. If you have thicker plate, thicker wall, then it's also stronger. And if you have, instead of 1 meter, if you have 20 meter height wall, then it's weaker. So, and you can calculate it. You can write an equal sign, and then you write the A modulus of the wall multiplied with the thickness of the wall and divided with the height of the wall. Okay, it's set for all elements. So it was something about 22%. I will run the calculation with the standard mesh. Only difference to the previous model is that we have used stiff or rigid supports, and now we have flexible support, we have springs. And you see we are better than with the rigid supports and after the mesh refinement. So we have 13% without mesh refinement. And if you do the mesh refinement now and run the calculation again, then become something around 10% of error. Okay, between 8 and 9%. So the springs in such plate models are very important, because if you have a rigid support, then you get very high gradient of stresses, and you get everywhere these singularities between the corners. Next thing is related a little bit also to beam. If you import the structure, then from for example IFC model, then if you look on the plate from the side view, then you have the plate with the axis, and then you have the wall. And you can say, okay, SCIA have this beam toolbox with the mesh with the automatic alignment. You can say, I do it, and then I go with the axis over the corner. So this is my mesh. Or you can say, I stay with the plate to the boundary of the structural model and only connect the wall to the plate. And what's the difference? If you connect the wall to the plate and you leave the plate, you have more advantage of after exporting of the reinforcement to your CAD program, because then you have the correct or the boundary from the structural model. What is the influence of on the accuracy? I have split this model to two layers. So first one is this on the left side. This will be calculated, and on the right side will be not calculated. So I run the calculation with the standard mesh of 40 centimeters. So I don't know if I have activated the, okay, the mesh refinement is activated. And we look at the accuracy of the model. 10%, not so bad. And if I switch it, this is deactivated and this one is activated on the right side. So that was 10%. Now run the calculation on the model on the right side. And we have 8%, so a little bit better. So these cantilever parts of the plates are not good for the accuracy, for the precision of the precision of the calculation. And then the next point is I see it often. For example, you have an elevator shaft, elevator room, and this elevator room have here the axis of the walls, and the plates are going to the inner boundary of this elevator room. And I see it very often at students that they don't move the nodes. They can do it with this beam toolbox, but usually they leave it. And if you look on the precision, I don't know if I have, okay, we will deactivate the right side. We have only the left side. Okay, run the calculation. There is also one hidden calculation. And okay, I have forgotten to activate the mesh refinement. So okay, now it's activated. Calculate the results again. And after then we see 12.5%. Look on the results and you see the precision of these elements is not very high. These are the most problematic elements in our slab. And you see how big should they. So they should be something below 8 centimeters, and we have 40 centimeters. So we can run the mesh refinement and fix it, but I will. So it was 12.5%. I hope I have it good in my brain. Okay, exchanged. Now we have the same walls, and only the boundary is moved to the axis of the wall. Calculate with the standard size, with the 40 centimeters. A little bit better, not so much, but after the mesh refinement it will be better. So this is also one of the points which will a little bit damage your calculation. I've calculated with it with the rigid supports. With the rigid supports you get a bigger difference, but also on this model the supports have influence on the calculation. So this cantilever part of the plates are not good for the precision of the calculation. Then some point supports on the slab, corners, and if you have, for example, two plates very near between the connection, so small distances, and one is going to the top, one is going to bottom. These are all points where you reduce the precision of your calculation. So you have the automatic mesh refinement. You can look on the problematic parts of the structure. Then if you don't want to use this automatic mesh refinement, simply look on the problematic parts. Then you can go to the calculation, to local mesh refinement, and you can do the mesh refinement also manually. You select the points, you select the areas where the mesh should be refined, and then you can do it on your way, but you know the accuracy and you know where are the problems.